I'll begin by describing or saying that the focus of SCEC research on blue waters is related to seismic hazard, developing improved seismic hazard estimates. So this picture tries to communicate the wide variety of observational data that needs to be considered to produce improved seismic hazard estimates. So we consider it a system science activity. It's very integrative. You need to bring these together, and many of these have computational models and other aspects behind them. But that's the focus, is to integrate various observations and scientific disciplines to produce a practical information on seismic hazards. So when we are asked why we need blue waters, there's a kind of extensive number of reasons, but, and many of them are common to other projects, but here are some of them. Our simulations are growing. People want larger regions. So instead of a simulation for Los Angeles, they want Southern California, or maybe the whole state of California, or higher resolution. And these drive our computational requirements up significantly. I like to express that in these type of seismic hazard calculations, you often need to rerun a problem. Basically, if you run a simulation and you get an answer, it's not a solved problem. Often you need to update it and rerun it with different inputs. So that significantly increases our need for computational time. And the third item is the push to higher frequencies. That's an important driver for the computational requirements in this field. So this is an explanation of both why we need higher frequencies and the computational costs as we go to higher frequencies. So this is kind of a rule of thumb, how you can tell which simulated frequencies affect what kind of level or story of building, which size of building. So if you're doing simulations at half a hertz, you're getting information, you're being informed maybe about 20-story buildings. But there aren't that many 20-story buildings. I mean, it's a small fraction of all the buildings in Los Angeles, for example. So it's important or needed to get to higher frequencies. So last year we were working at half a hertz for our probabilistic, and this year we're going to, I'll show you some results for 1 hertz. And so this now is better. It'll inform us about 10-story buildings. But where we really need to go, where the majority of buildings are 1-stories or single-family dwellings. And so we need to continue to push the frequencies that we're simulating to these higher frequencies. And at the bottom, we'll point out that in some of our methods, such as finite difference methods, as you double a frequency, it's a 16-time increase in computational work. So you need to double X, Y, Z, and T, and you get a 16-time increase. So this is driving our need for more computational as well. A couple of other items. It's a system science program, broad range of different types of computation are being done, CPU, GPU, data intensive workflows, all of those, and Blue Waters is very good at supporting all of those. We also have the issue of how long it takes to complete an important calculation. We call it the time to solution. And our perspective is we need to solve some of these problems within a reasonable length of time. If it takes even multiple months, it becomes impractical. So this is a slide showing in some sense a variety of the different types of simulations and the different codes that are involved. To highlight one of the previous point, but this is talks a little bit about some of our computational time and what we either the make span or time to solution. This is a seismic hazard calculation that we've repeated several times with different input. And even when we got onto Blue Waters, we split the calculation between Blue Waters and Stampede. It took 61 days, 2 months to complete that calculation. And that's right at the level where we can keep the staff engaged and so more time than that is problematic. So the time to solution, how long it takes to complete a calculation is an important consideration for us. This is the inference spiral of system science that Tom Jordan, my boss, likes to talk about. And it's very true that this is a kind of an iterative process that our research is going through. You develop kind of new conceptual models, you do simulations, you compare the results against observation, and then you do a data assimilation to, and basically to restart the cycle. And we are going through this cycle repeatedly over the last decade or so. So as far as particulars, these are 3 work areas and results this year or over the last year since the last Blue Waters meeting that we've produced. So the basic ideas are the work areas have been integrating new physics into our ground motion simulation, push our simulation codes to higher frequencies, and push our ensemble or probabilistic simulations to higher frequencies as well. So this is an example of integrating new physics and developing in some sense more conceptual models, new conceptual, improved conceptual models for our simulations. What we found is as we push to higher frequencies, we start to observe effects that were not important at low frequencies now do become important. And there's kind of a list here, or there's a list here of different characteristics that are now we need to take into consideration, and we need to take to modify the physics codes to take these into consideration. Near fault plasticity, nonlinearity. So this is one of the work areas that we spent time on this year. This is an example of one of those where we're improving the physics and experimenting with new ideas and new ways to model earthquakes. This is an example of 2 different alternatives, ways that earthquakes might rupture. How quickly is the energy released? And we don't know the exact correct answer, so we come up with some alternatives. And so that's part of this inference spiral. So this is a kind of a new conceptual model. And then we do some simulations and evaluate how well do these new approaches work. Does one work better than the other? Which one seems to be most appropriate? So once we've got kind of a new working model, the next step is to compare it against observations. And seismology, particularly these ground motion simulations, have the great benefit that we have good observations and we can simulate historic events, and we can compare our simulation against what was observed for those events. And this is an example of doing that, or the kind of event we would use. This shows Los Angeles area, and the green dots are stations where we have ground motion observations. And so this was a common activity for us. We'll have a new physics integrated into our code, and then we'll rerun this event. And then we'll compare our simulated ground motions against the observations. And that helps inform us and tell us, are our models working better? So, and this is an example of kind of a result we would get from that activity. These are include some simulations that were done on Blue Waters. And we're comparing different Earth structure models. And up in the top left is what the observation. This is a recorded earthquake. So we have these observations from that earthquake. And then we've got these different alternative Earth structures. And we're trying to identify which of these Earth structures best reproduce the observed data. And that informs us and tells us which Earth structure is most likely correct. So this year, an important push for us was to go to higher frequencies. So the key idea that I want to express is that we run simulations in some sense in 2 modes. We have individual earthquake simulations, and these kind of lead the way. This is where we integrate the new physics. We push them to higher frequencies. We do the validations, the careful validations against observed earthquakes. So these are kind of the leading edge of our simulation program. But for the broader impact and the information used by engineering community, they don't want information from a single earthquake. They want an ensemble. They want probabilistic information. So we need to simulate literally hundreds of thousands of earthquakes. And to run at that scale, we can't run at the same frequency. The cost would be too high. And this gives, so this year we did both. We increased the frequency on individual earthquake simulation. We also increased the frequencies that we're simulating in our ensembles. And it shows in the bottom, in some sense, how much the ensembles lag the single event. So for single events, we're working at 4 hertz. And for the ensembles, we're working at 1 hertz. Eventually, we'll be able to, when we have confidence in the 4 hertz results from a single event, we'll integrate those codes back into our ensembles. So this is an example. This is results from Blue Waters, 2 alternative codes. One of the ideas, simulations in seismology, probably other fields, gain credibility if they can be reproduced by other methods or by multiple methods. And so we often have alternative codes. They can use different methods. In this case, it's a finite difference method code and a finite element method. We use them to run the same problem. We expect them to produce equivalent or the same result. And so this is an example of doing that. We ran both codes on Blue Waters. These are on the CPU cores. The finite difference simulation was configured like this. It has a regular mesh, and this is a finite element simulation, significantly fewer cores, smaller number of elements. I'll point out kind of how finely we're discretizing the California region. So on this finite difference, it's a 20-meter resolution. So we discretize the Earth to 20 meter, and that's quite fine resolution. And the finite element gives you some variability, so they have even finer resolution in some places and larger resolution in others. So at the end, we get a result something like this. This came out last week sometime. This is seismograms from the same station using different codes, and it's promising that the time series look quite similar. So we expect them to be essentially identical. We do see some differences. The amplitudes are different. This is higher amplitude up here than down here. So it's not an exact match, but it's a promising first step because this is at higher frequencies than we've run previously. And then our third major work area this year was on these ensemble, increasing the frequencies for our ensemble simulations. And so this is where I wanted to bring in the real world, as I mentioned in my topic. Not to say that Blue Waters isn't in the real world, but programs running in memory may not. It's not clear how they have an impact, but this is our, in some sense, explanation and description of how these ensemble calculations, we believe they can have a significant impact. So this points out that this is in the news, the LA Times. There's a new proposed rule, I guess, law within Los Angeles that the cell phone towers should be built strong enough so that they continue to operate after an earthquake. So that's a change. In the past, in the current codes, basically it requires they're strong enough so they don't fall down and hurt anyone. But the new requirement is they need to be stronger so that they can continue to work after the earthquake. So the question is, where do they get the information to identify how strong these towers need to be built? SCEC works on providing estimates of the ground motions, what ground motions these towers would need to survive to continue to operate. So I'll point out the City of LA has a new resiliency plan. Their recommendations, I think, are very well thought out, but can be quickly summarized as strengthen our buildings, fortify our water system, and and enhance reliable telecommunications. So I think that's a recognition of how important communications are during emergencies. To us, this is moving us. SCEC typically works in the domain of seismic hazard, which are estimating the ground motions. This is moving into the area of seismic risk, saying for a given set of ground motion, will this structure be damaged? And so this is an example. If these two structures were subjected to the same ground motions, which has a higher risk? So probably this multi-story house would be at higher risk and be more likely to be damaged. So even though the hazard might be the same, the risk would be different. So what we're seeing is this idea and the development that SCEC results are being considered for use in this broad impact area on this idea of building codes. So we're learning, in some sense, how these results, or what the path is from blue waters into this broad impact usage. And this seems to be the path that we understand. And it's a plausible path, and we're very happy that, that we've been engaged with the engineers, and we're beginning to go down this road. So the way we anticipate it will work, or can work, we use blue waters to calculate improved peak ground motion. These are used by the engineers to identify the maximum credible ground motions at different locations in Los Angeles. Then an engineering society, the American Society of Civil Engineers, use that new information and put it into their building code recommendations. Then public authorities, they typically don't write their own building codes. They reference a recommended set of building codes, such as the ASCE codes. And then that becomes the code in the city. And then the people building new cell phone towers are informed by that information, by the maximum credible ground motions identified in those codes. So if SCEC contributed to those improved ground motion estimates, and we go through this processing, then we can make a reasonable case that Blue Water's results contributed to a safer environment. And really that's the impact that we're working toward. So I focused on cell phone towers as just an example because that's been in the news, but point out that if we go down this path and this becomes fact, that it would impact all of the construction in Los Angeles. And there's over $5.3 billion worth of construction permits in 2014 for Los Angeles. And these codes would impact all of those. So this is how we try to express the impact of Blue Water's research on the broader world. So just to summarize the results that we have so far on this, the kind of calculation and the information that we calculate are these seismic hazard maps, or maps like these. These are seismic hazard maps. This points out that the maps are updated on a regular cycle, on a 5-year cycle. And so this work, even when we produce a new seismic hazard model next year, we're not done. They'll need to be updated in another 5 years. SCEC has a computational method. These are the official USGS maps. SCEC's computational adds in more physics. So it's more computationally intensive than the existing methods that are used by the USGS, but they produce more accurate results. That's why the engineers are interested, because they get additional information if they make use of this computationally intensive approach to seismic hazard. On the current simulations, point out some of the type of issues that have come up, or things like this. How are hypocenters distributed along a fault? So it's an important issue. Part of our simulations is to simulate all possible earthquakes that might happen on a fault. And so this gives an idea of how we might distribute the hypocenters. These are specifications on the simulation that we began earlier this year on Blue Waters. This is kind of some more specifications on the simulation. It has a large GPU portion, And some of that we're running on Titan. We're moving the results over for final processing to Blue Waters. We're also using the GPUs on Blue Waters and doing the full workflow on Blue Waters. But the scale of this is that we're using 2 leadership class to get through this. Over a petabyte of temporary data, 40 million computer hours. And it's approximately half done. It's a little over half done as earlier this morning. What we found is, or one of the aspects of these models is you can decompose it. You start with a map and you can work your way down into ground motion seismograms. The engineers have communicated to us that now, because we have these seismograms, they can recompose and they can calculate their own seismic hazard or their risk-based information. These were calculations we did not do, the seismologists did not do, but users of these hazard models have identified this series of calculations that they're interested in doing, and we're able to support those with these results. This engagement with the engineering community has been very good. They're communicating clearly exactly what they need and want from us. This was an example 6 months ago. We met with the engineers and did the initial engineering-related calculations. And we had a meeting 2 weeks ago with them where we followed up and we presented the recent results from the current study for them 2 weeks ago. And as one example, this is the map of Los Angeles. We look at a seismic hazard at one of the sites. I think it's the yellow dot down there in the center of Los Angeles. And without going into explanation, this is a new result. So as of last year, this is the estimate of the seismic hazard. It's a way of estimating seismic hazard at this site. And a new result, the seismic hazard has changed. So, and the expectation is that the new result in our study this year is more correct. So these are the type of products that the engineers want. This is a seismic, or the type of engineering map using the CyberShake method. This is the existing one that they currently use, and this gives an idea of the differences between them. And basically the idea is the areas in red are anticipate or need to anticipate stronger ground motions if the CyberShake results are correct. So this is in some sense the delta that, and the additional new information that you get with the computational intensive method we use. But it's also worth pointing out that the estimates don't always go up. In some cases, the hazards and the expected ground motions go down. So I'll conclude with pointing out, we're very excited about this work with the engineers. We've moved from some sense academic, kind of curiosity-driven research to important computational data products used by engineers in things like building codes. But it depends very heavily on the computational infrastructure and the resources that are currently available. So we want to emphasize this work and this impact of computational science on the real world can be done, but at least for SCEC, it's not yet done. So we need continued support for supercomputer centers like Blue Waters, support for high-performance scientific software developers, support for geoscientific research, and multidisciplinary collaborations that involve both scientists and engineers. So with that, I'll close. Good, thanks.
All right, so we're up against lunch right now. So could probably entertain a few questions from anyone in the audience, if there are any questions. Oh, Celso. Oh, use the mic this time.
So on Titan, are you using the GPUs?
Yes, yes.
And the code, when the code uses the GPU, it uses only the GPU?
That's correct. We've done some investigation what we call co-scheduling. So in our workflows, we have a large parallel portion where we're running on the GPUs, but we have some post-processing that only runs on the CPUs. And we've done some proof of concept that We could schedule a parallel part on the GPU, and then we could co-schedule the post-processing on the CPU. We've shown it's possible. We haven't integrated it into our production environment yet.
All right. Thank you. Any, oh. Okay, Jeremy.
So you mentioned that the codes are created by, based on the maximum credible ground motion. So does that impact which model you select? Is it more biased towards the whichever one is showing the worst case scenario, or whichever one is actually matching the reality most accurately?
So that's a good question, and it gets into, in some sense, how we deal with the uncertainties in these models. Maybe the short answer is that when we have alternative approaches, or let's say alternative Earth structure models, and we're really not sure which one's correct, the engineers will develop a logic tree, and they'll weight. They'll say, we want both calculations, and then they'll give appropriate weight, in some sense, a confidence level, saying, here's a result produced with Earth structure A. We have slightly lower confidence level that result is correct. We'll give it a 25% weight. This Earth structure model we think is more correct. We'll give it a 75% weight. So that is one of the ways they deal with the alternatives. But typically what they ask for us is the full spectrum. They want to see all of the available results. The engineers don't want us to pick which one's correct. They want to see what the uncertainties are.
All right. If there aren't any more questions, let's thank the speaker one more time.